Okay, so welcome remote learners to lesson 4 in our energy changes unit of work. I hope that you've now got a good understanding of reaction profile diagrams that we covered in lesson 3. Just a reminder for you that this is where you will find it. At the time of recording this video, no one has yet completed questions 1 and 2 that is part of the task. So please do make sure that you use those to assess your understanding of how we represent endo and exothermic reactions in this way. So the first thing I'd like you to do, please, is have a look at task 1. So what I'd like you to do is complete the sentences by choosing the correct word from the options in the following sentences. So if you pause the video now and then restart the video once you have had a go, and we will have a look at the correct answers. So if you pause the video now. Okay, so hopefully you have managed to identify the correct words in each of the sentences. So we should have chosen the following: in a chemical change, reactant bonds are broken and new substances are made as product bonds are made. So we are breaking bonds and then making bonds. Breaking bonds takes in energy from the surroundings, and this is an endothermic change. Making bonds conversely releases energy into the surroundings, and this is an exothermic change. So those are the answers that you should have to the following sentences. Remember that atoms are held together in chemical bonds by opposite forces of attraction. So because they are being held together in such a way, you need to put energy into the system from the surroundings in order to break the bond, and the reverse happens when you make chemical bonds. So now I'd like you to have a look at task 2. Look at the chemical reaction occurring below. So we're looking at this reaction here. The diagram shows the displayed formulae, so that's showing all the chemical bonds. So for example, one of these lines here is a chemical bond. In fact, it is a covalent bond. Okay, for the reactants and products. So can you label them first? So which are the reactants, which are the products? Can you name them? So you might have to have a look on the internet, although I think 3 out of the 4 are very, very straightforward, e.g. this is O2, so what is that? What must happen to the bonds in the reactants for them to become products? And as an extension, can you use the information in the diagram to write a balanced symbol equation for the combustion of methane? So there's a little bit of a clue there as to what reaction is occurring. So if you pause the video now, have a go at task 2 and resume when you are done. So hopefully you've managed to identify the reactants on the left-hand side of the arrow. So these are the reactants, and of course on the right-hand side of the arrow, these are the products. So we've done A. Can you name each of them? Well, you can see here that this molecule here is made up of 1 carbon atom and 4 hydrogen atoms, and perhaps that's not one that you've come across before. That is indeed methane. O2 is, of course, oxygen. Here we've got CO2, or carbon dioxide, to form H2O, which is water. So we are reacting methane plus oxygen to form carbon dioxide plus water. This is the combustion of methane, and you know from your prior knowledge that combustion reactions are exothermic. Now, what must happen to the bonds in the reactants for them to become products? Well, we can see that even though we've got the same number of atoms of each element on either side of the equation, they're arranged in a different way. So we know here that the bonds must have broken. So bonds must be broken, and you can see over here that the bonds are then reformed. Can you use the information in the diagram to write a balanced symbol equation for the combustion of methane? Well, we can take our chemical formulae that we've got. So we've got CH4 plus O2. Now we can see from the diagram that we've actually got two molecules of O2. We've got one there, so there's a big 2 in front of our oxygen to form CO2, and we've only got one of those plus 2 H2O. And you can see from the diagram we've got one there and one there, so it's 2 H2O. And if we're to count up the number of atoms on either side, we can see that this is balanced. We've got one carbon on the left, one carbon on the right, 4 hydrogens. There's 4 hydrogens on the product side as well, and then we've got 4 oxygens in total because this is 2 times O2, which is equal to 4 oxygen atoms, and then we've got 2 coming from the carbon dioxide and 2 coming from the water, so there's 4 oxygens on this side as well. So that is your balanced symbol equation for the combustion of methane, which, as I said, was an extension. So, okay, well, what are we going to do with this this information? Why am I displaying this reaction in this way? Well, we need to use it so that we can do something called a bond energy calculation, and that's what we're going to be focusing on. I want you to have a look at the 3 images below. So image 1, image 2, and image 3. I want you to tell me what type of bonding do the following images show. So think back, you've got 3 options. Is it ionic, covalent, or metallic? What is the similarity in all situations? What is the difference between them? And which bond do you think requires the most energy to break? So again, pause the video now, have a go at answering those questions, and we will resume shortly. Okay, so hopefully we have managed to work out the answers to these questions. Now, what type of bonding is being shown here? It is covalent bonding. We know this because covalent bonding occurs between non-metal and non-metal atoms, and we know that carbon is a non-metal. The similarity is that it's showing covalent bonding between 2 carbon atoms. But the difference is that in this case, in image 1, we've got a single covalent bond. In image 2, we have a double covalent bond. And in image 3, we have a triple covalent bond. Now that means there's only 1 pair of electrons being shared in this example. There are 2 pairs of electrons being shared. And in a triple bond, there are 3 pairs of electrons being shared. And which bond do you think requires the most energy to break? Well, probably we're going to identify that this triple bond here that's sharing 3 pairs of electrons is the bond that's going to require the most energy to break, because the forces of attraction holding those 2 carbon atoms together is the strongest. So that was image 3 there. And essentially what we're leading on to is to answer this question. How much energy do I need to put in to break the bond? I'm going to put how much energy is required to be transferred from the surroundings, remembering this is an endothermic process, now different amounts of energy are required for different bonds, and if you were asked to define the term bond energy, it is this: the energy needed to break the bond between 2 atoms. Okay, it's called the bond energy. We measure this in kilojoule per mole, and that's because what we are actually doing is how much energy is required to break a mole of these bonds, but you don't need to worry too much about that at this stage, because you're essentially going to be doing that in your calculations using your balanced symbol equations. And what we can do, I'll just put units of bond energy. What you can do is use these bond energies to work out the energy changes for many chemical reactions. So you are given this table. I've put a little note here, do not panic. You will be given this table of values in the exam. Here are the common bond energies that we need to be able to use. So for example, a CC bond that we were looking at above requires 347 kilojoule per mole of carbon-carbon bonds to break that bond. However, for example, a hydrogen bond, HH, requires 436 kilojoule per mole. So we could say that the HH bond here is stronger than the CC bond, and that's because it requires more energy per mole to break. Okay, so let's have a look at how we use these in an exam. And we're going to return to the equation that we were using before, the combustion of methane. So we are going to work out the overall energy change occurring in this reaction. And the nice little equation that we're going to use is that the overall energy change is equal to the energy required to break bonds, so bonds broken, minus bonds made. Okay, the energy required to break bonds minus the energy required to make bonds. And you can help yourself remember which way around it goes, because we've got breaking bonds over here, okay, minus making bonds on the right side of the arrow. So we need to know how much energy is needed to break all of these bonds. So we've got all of these in front of us here. So for example, I'm going to highlight every single bond that we need to break. Okay, I'm going to highlight that in green. And how much energy is released when new bonds are formed. Okay, so making bonds, we've got to look at this bond and this bond, 1, 2, and all of those bonds there. So we need to account for every single bond. I'm going to put this here. Account for every single bond you see. Okay, so it's quite really important that you make sure that if you've got 2 moles of oxygen or 2 2O2, that you're making sure you're breaking 2 of those bonds. So overall energy change is energy required to break bonds minus energy required to make bonds. Now, let's have a look then at how we're going to do this. So we need to use this information in the table. So first of all, I can see that I've got 1, 2, 3, 4 CH bonds. And a CH bond from the table is this bond here, 413 kilojoule per mole. So I know I've got 4 times 413. Okay, and if I put that into my calculator, 4 times 413 is equal to 1,652. So that is the energy required to break all of those carbon-hydrogen bonds. Whereas the O2 bond, so here, okay, you can see it's got that double covalent bond, is 498. Now, how many have I got of those? I've got 1, 2. What value was it? 498. So I've got 2 times 498, which is equal to 996. Okay, so the total energy required to break bonds here is equal to 1,652 plus 996 minus, okay, now let's have a look at what we've got on this side. So we've got 1, 2 CO bonds. So let's have a look in the table. Oh, we don't actually have a value for that. That's infuriating. I'll quickly look it up. Hold on for 1 second. You will be given all of the information that you need, but unfortunately I've picked an example where you haven't. Okay, 799 for one of those. So how many have we got? We've got 2, so 2 times 799, which is equal to 1,598. So put that in there, 1,598 plus, well, how many OH bonds have I got? Well, I've got 1, 2, 3, 4. Okay, so we need to find the HO, which is 464. So 4 times 464, which is equal to 1,856. So 1856. And then I put this into my calculator and I add those two brackets together. So if I do the following, and if you'd like to follow and make sure you're getting the same answer, always checking for calculator error, gives me minus 806 kilojoule per mole. Now that minus sign you should be able to identify, that means there is a negative overall energy change. Okay, so therefore this is an example of an exothermic reaction. Now let's just sort of contextualize how we know that's exothermic. We remember that if energy is released to the surroundings, if I just sketch this on a reaction profile diagram, okay, we've got our reactants, put up our activation energy in, and our products. Okay, just a reminder that the overall energy change is negative if it is an exothermic reaction. So here, if we were to sketch a graph for this, we would be able to say that the overall energy change is minus 806 kilojoule per mole. Okay, so more energy was released when making bonds than energy put in to break bonds. Okay, which is why we've ended up with this negative sign here. So I've left you with some top tips. Do have a look over these to sort of help you with these questions. I've just sketched that reaction profile diagram over there. So have a watch of the video, and then I will add some questions below for you to have a go at. Please do complete those questions by the deadline on this assignment. So I hope that helps there for you.